All right, well, I'm going to stay in here and talk to myself then. The last thing I talked about with chairs was the chair flip, um, which is when one side of the chair flips up, the other side flips down, and you interconvert all the axial and equatorial substituents, but you don't interconvert the up and down substituents. Um, I have two tips for you if you're trying to learn to draw the chair flip. There are two different ways you could do. I mean, there's actually like 48 different ways you could do it, but two different ways I would conceptualize it. One is what I call the actual flip. In the actual flip, all you're doing is you're drawing it as it actually appears when you do the flip. If you flip one side up and one side down. So if you start with a chair that leans to the right, you're going to end up with a chair that leans to the left because you're going to flip the left side up and you're going to flip the right side down. That's why I call this the actual flip. You keep the far left and far right carbon atoms the same. So if I were to number these and put a 1 on the left side and a 4 on the right side, 1 is still going to be my far left atom. 4 is still going to be my far right atom. But now I'm going to draw a left-leaning chair. So for a left-leaning chair, it's going to look like that. 1 is still on the far left, but now it's going up. 4 is still on the far right, but now it's going down. And then I would just add in my substituents. So on 4 I have bromine going down. It'll now become axial. On 1, oh sorry, not on 4. On 5 I have a bromine. Forget everything I said in the last 15 seconds. On 5 I have a bromine, and it's going up. So now it is going to become axial. On 1 I have a methyl group. It's going down. It will now be equatorial. And on 2, I have a chlorine. It is up. It will now be equatorial. And if I want to get fancy, I can put in the little break behind the bromine to show that the bromine is in front. At home, I'm sure you're oohing and ahhing. All right, so that is drawing the one way to draw the chair flip. It's a way that visually represents the chair flip probably better, but is more challenging to do. The easier way is a way that doesn't look like you're actually doing a chair flip, but effectively gets you to the same place and is easier to follow. So in this case, you're just rotating your viewpoint. You would draw the same chair you drew before, but you would just move each substituent clockwise or counterclockwise by one spot, and then you switch axial to equatorial. So to demonstrate that with this same molecule, 1, 2, 3, 4, 5, 6, I'd say, oh, I don't like drawing chairs that lean to the left, so I'm just going to draw a chair that leans to the right again. And I'm just going to rotate all my numbers. So now I'm going to rotate number 1, say, to up here. Number 2 to here. Oops. 3, 4, 5, and 6. So I rotated everything by one position. The methyl group that's on carbon 1 goes down. That is now going to be equatorial. The chlorine that's on carbon 2 goes up. That is now going to be equatorial. And the bromine that's on carbon 5 is up. That's now going to be axial. I didn't actually draw. I didn't give myself enough space over there. So I'm going to have to do the short axial bond and put the bromine here. Not as fancy. I definitely think the other drawing was better. But this one gets me to the same point. So those are my tips for how to draw the chair flip. Questions? All right. Um, and then if you're looking for tips for translating between planar and chair, the key things are keep all the clockwise relationships the same. So anything where if you number your planar projection clockwise, you should number your chair clockwise. If you number counterclockwise, number your chair counterclockwise. Wedged bonds go up and dashed bonds go down. And the reason for that, if you take your model and you look at it so that you're looking at a flat hexagon, and then you shift your view to see the chair, what you'll see is that all the things that were coming towards you in the flat projection are now going to be going up in the chair. So, as an example, give yourself a moment to try and draw the chair of this molecule. Pause while you do it. So I chose to number my ring starting with where the methyl group was and going clockwise. You could choose wherever you want. That's one arbitrary choice you have to make. Then the one other arbitrary choice you have to make is to choose which carbon you want to be carbon 1 in your other ring. And you could choose any of them, which means you have 6 choices. It's really up to you. I'm probably going to choose to call number 1 my left-hand carbon and then go around clockwise. So this would be 2, 3, 4, 5, and 6. So on carbon 1, there's a methyl group. It's a wedge, so it's going up. On carbon 1 is up axial or equatorial. So carbon 1, the 2 bonds make a point that points down. So axial will be down, equatorial will be up. It'll be parallel to the 2, 3, and 6, 5 bonds. And then on carbon 3, notice the 2 bonds that make carbon 3, that come together at carbon 3, do they point down or up? Down. So down there for the bromine is going to be axial. And I can put in the little break and put my bromine there. All right, so the question is, could I switch that? Yes. If I had just made the arbitrary choice to change which carbon was carbon 1, like which other carbon could I choose as carbon 1? Bottom one on the right here. Yep. If I choose this as carbon 1, then I number clockwise around 1, 2, 3, 4, 5, 6. On carbon 1, my methyl group is up. Well, the 2 bonds that make carbon 1 are pointed down, so up is going to be equatorial. 3, the 2 bonds that make it are down, so down is going to be axial. So based on my arbitrary choice, that's going to tell me where my substituents end up. Now, if I just rotate my arbitrary choice by 1 point, rather than moving by 2 positions, if I make this carbon 1 here 3, 4, 5, 6, 7, then based on that arbitrary choice, I'll get the flipped version of the chair, where now on carbon 1, the up substituent, the methyl group, would be axial, and on carbon 3, the down substituent would be equatorial. So all 3 of these represent the same molecule. You know, you could come up with like 48 different correct representations of the molecule. So then the question is, you know, which one is a more stable conformation? The 2 at the bottom both represent the same conformation. The one at the top represents a different conformation. So these are the same conformation. whereas the one on the top is a different conformation. And we could decide which of those two is the more stable chair conformation. To do that, we'd have to know that, well, a methyl group actually takes up a little more space than a bromine. So having methyl group equatorial is more important than having bromine equatorial. So these two are actually the more stable conformation. This one at the top is a little less stable. But you need the information that methyl is bigger than bromine to answer that question. All right, so the question is, why does being bigger make it more stable? Aha. So this actually, I'll talk about at the end. But it turns out being in the axial positions, if you look at the model, there's a little less space for things in the axial positions. So big groups tend to prefer equatorial positions so that they don't bump into other things. Here's one more example to try. So if you're watching at home, pause it, try this out. Here we're translating from a chair structure to a planar structure. So I'd start by drawing a hexagon and numbering around my ring. And then I'm just going to make the arbitrary choice of which carbon to call carbon number 1 in my hexagon on the right. Doesn't really matter. All right, so carbon 1 has what kind of substituent coming off of it? Carbon 1, that's equatorial. Is it going up or down? It's up. It's going up at an angle. So that's going to be a wedge. And it's an isopropyl group, so I'm going to draw those two other groups branching off. Carbons 2 and 3 have no substituents. Carbon 4, is that substituent up or down? Up. So that's also going to be a wedge to a methyl group. Carbon 5, well, I've got one group up and one group down, so I'm going to have a wedge and a dash. What goes on the wedge? OH, because that's up. Methyl goes on the dash because that's down. And then carbon 6 has a bromine also pointed up, so that's going to be a wedge. So doing that translation, you just follow those rules, and it's pretty straightforward. And don't get hung up on the fact that you make an arbitrary choice and there's lots of correct ways to draw the answer. So one final example for you to try. Again, pause it if you're at home. Draw your structure, and then check. And just for fun, I'm going to draw one chair drawing, and then I'm going to draw the flipped chair drawing so we see both conformations. All right, so on carbon 1, I've put an ethyl group. It's a dash, so it should go down based on what I've chosen as carbon 1 over here. Those two come together to make a point, going down. So that ethyl group is going to be axial down. Carbon 2, I have a methyl group that's down. Well, if axial was down on carbon 1, equatorial is going to be down on carbon 2, so that'll go down at an angle like this. Carbon 3 has no substituent. Carbon 4 has an SH group that is pointed up because it's a wedge. And on this carbon, up is going to be axial. Carbon 5 has no substituent. On carbon 6, there's a chlorine that's going to be down, which is equatorial there. So that's one drawing. If I flip it, I'm going to do the actual flip here. Drew the left-leaning chair. Carbon 1 still on the far left. Carbon 4 still on the far right. Now on carbon 1, I have the ethyl group down. That's going to be equatorial now. Carbon 2, the methyl group down is going to be axial. Carbon 3, no substituent. Carbon 4, the SH is going to be up and it's going to be equatorial. And carbon 6, the chlorine is going to be down and it's going to be axial. All right. So just something you practice. So then the last topic is just how do we know what's more stable? I already mentioned this, but the idea is things in the axial position. Turns out they bump into each other a lot. The groups in the axial position, if you look at your model and start putting groups in the axial position, they end up hanging out over the middle of that ring and bumping into the hydrogens on it. So you want to try and minimize the number of axial substituents. And also, the bigger the group, the greater its preference for being equatorial. And if you ever have a tert-butyl group, that almost locks the chair so that it can't even go into the axial position. It's so unfavorable. So, two last examples. This one here, and I'll draw the one on the next slide so that you can look at them both at the same time, copy them, and then make your attempt at drawing both chairs and choosing the more stable one. All right, so I chose to number a particular way. You may have chosen to number another way. I usually try and choose it so that I like carbon 1 to be my left-hand carbon in my chair, and I try and choose it so that I don't have substituents on 2 and 3 in the back, because those tend to give me more trouble. You'll figure out what makes the most sense for you. So on carbon 1, I've got a tert-butyl group that's going to be up. So that's in the equatorial position. On carbon 4, methyl group that's down, that's in the equatorial position. And then bromine on carbon 5 is going to be down, that's going to be axial. If I flip, I chose to do the rotated viewpoint flip. You could have chosen to do the actual flip as well. If I do the flip, then now my tert-butyl group becomes axial. On carbon 4, my methyl group becomes axial. On carbon 5, my bromine would be equatorial. And between these two, this one on the left would probably represent like 99.99% of molecules would be in that conformation because it's way more stable. You might ask why we care about that. Well, stability of conformations, it turns out for certain reactions, the molecule has to be in a certain conformation for the reaction to occur. And so this particular molecule, there's certain reactions that it could undergo because the bromine is in the axial position, but the bromine is almost never in the equatorial position. So any reaction where you wanted bromine in the equatorial position wouldn't be able to happen. For this next molecule, here we've got, again, I chose not to have substituents on my back carbon, so carbon 4 has got a methyl group that's going to be equatorial, so it goes down. Carbon 5, an ethyl group, that's going to be equatorial, so that goes down. And then carbon 6 has a methyl group that's up, so that's going to be axial. And I could choose to put in the little break if I want to be fancy. And then if I switch my, I forgot to rotate. Maybe I'll draw the actual flip this time, just for variety's sake. So now I'll draw a left-leaning chair. I'll keep carbon 1 on the left and carbon 4 on the right. And so my substituents are on carbons 4, 5, and 6. 4 down is going to be axial. 5 up is going to be axial. And then 6 down, up is going to be equatorial. Again, I could put in the little break here. And choosing between those two, the one with 2 substituents, equatorial, is going to be more stable than the one with 2 substituents, axial. And that'll do it for chair conformations. This concludes the lecture. This also concludes the portion of the course where you're thinking just about structure of molecules. From here on, it's about reactions.